It's chemistry and you are watching Chem Science.
In this video, let's study the analytical chemistry topic NMR. So what is NMR? We'll be learning that. Then what is TMS? And then we will be observing the NMR of some compounds. That is, we'll be analyzing and studying the NMR of some organic compounds by the end of this video. So let's first see what is an NMR. NMR denotes the nuclear magnetic resonance, which is a type of spectroscopy which we have also earlier studied. And what is NMR used for? NMR provides us some information about the structure of an organic molecule or useful technique of the analytical chemistry. Now, NMR is generally used to analyze the organic compounds, and the full form of NMR is nuclear magnetic resonance. Now let's understand what is NMR and how does it work. Now let's first understand one point, that the nuclei, that is the nucleus of each and every atom, possess some charge and mass. We know the charge is positive charge and it has some mass. But the nuclei with the odd mass possess the spin. Why only the odd mass? Because the one with the even mass number will cancel each other's, the nuclei, the protons inside the nucleus will cancel each other's spin. But the one with the odd number will not be able to do so, and then it will possess some kind of spin. For example, here we can see that the hydrogen has the atomic number and mass number 1. Carbon with the 13 mass number, not the C12. C13 will possess the spin. Similarly, fluorine with the atomic number 19, which is again an odd number. Phosphorus with 31 mass number, again that's an odd number. So such nuclei of these elements will possess the spin and then can be easily analyzed under the NMR spectroscopy. But other nuclei like carbon 12 or hydrogen with the odd mass, even mass number of 2, that we also call it as deuterium, such hydrogen or carbon will not possess the spin. Only the hydrogen with the mass number 1 and carbon with the mass number 13 and the other elements with the odd mass number will be possessing the spin. Now in this technique, how do we analyze the compound with such an NMR technique? Now what is done? The first thing is the sample of the compound is spun in an external magnetic field. So some kind of external magnetic field is applied on the compound. Here we can see the picture of this NMR spectrometer where a compound is taken in a tube and then it is connected with a magnet. It's kept in between the external magnetic field and then it is analyzed by also radio frequency, that is RF field, which we also say as radio frequency field. This is applied and then the compound is detected with the help of a data analoger, where we can see that this spin will produce some kind of peak as it is shown here, and these peaks are analyzed for the various types of functional groups or the elements present in the compound, and this will give us an idea of the structure of a compound. Now, how does a compound behaves in an external magnetic field and it produces various kinds of peaks? If we say a spinning nucleus such as hydrogen 1 behaves as a spinning charge and generates a magnetic field. Now what happens here, that hydrogen has just one proton, so that one proton itself will behave like a bar magnet, and then it will behave in some way, react to some way in the external magnetic field. So when an external magnetic field is applied, then what happens? The tiny magnet of the hydrogen, that is the tiny proton of the hydrogen which acts as a magnet, will either align with the external magnetic field or it will align against the external magnetic field. But actually what happens, it keeps on spinning with and against the external magnetic field. Both is going to happen, and then it will be flipping between the two different energies in that case, and the energy difference between these, the aligning against the magnetic field and the alignment with the magnetic field. Why? Because the alignment with the magnetic field will have a lower energy, and when the proton will align against the magnetic field, external magnetic field, then it will have a higher energy level here, and the difference between this energy corresponds to delta E. Now these delta E is responsible for the behavior of the proton, that is the tiny magnet which acts, and then it's going to produce some kind of spin, and then it will produce a peak which can be analyzed by the data logger. Now suppose the compound which we want to analyze is a solid, then how are we going to pass the external magnetic field and how is it going to behave? So what is done is that such solid compounds are dissolved in a deuterated solvents, that is, you can call it as, one example is CdCl3, that is the normal hydrogen is replaced by a deuterated hydrogen, that is, we have already seen that hydrogen can have a mass number of 2 also. Such an hydrogen is also called deuterium. So the normal hydrogen is replaced by deuterium, and then such an liquid, such an solvent is used, or we can also use another solvent, that is tetrachloromethane, which doesn't have hydrogen. Now why is this needed? Because the solvent should not have a normal hydrogen, because that is also going to produce a peak, now which is going to hinder the analysis of our compound. So that's the reason that the solvent should not produce any kind of peak, and so we use an inert solvent like deuterated solvent or a solvent without hydrogen, for example tetrachloromethane, as we have shown here. Now what is a TMS? TMS is tetramethylsilane. Tetramethylsilane is also pronounced at times. Now what is this? This is added to provide a reference signal for our compound. Now first let's study the structure of tetramethylsilane, that is, a silane is a silicon element which is bonded to 4 other methyl group. That's why we call it as tetramethylsilane. And now we can see that there are total of 12 hydrogen, which number is big enough to produce a very sharp peak. Because there are 12 hydrogen all together, it's going to produce a very sharp peak and a very high peak, and a single peak is produced. The reason being is that all these 12 hydrogen are in the same environment. Now that we'll study in the later part of this video, that what do we mean by the environment. But here we can understand that the 12 hydrogen together of the same environment is going to produce a very sharp and high signal, and that can be used as a reference in the sense, this we will give a number of 0 ppm. So here this peak will be used as a reference with the 0 number. And why do we use TMS? TMS is tetramethylsilane, is non-toxic also because it doesn't affect any compound and it is inert, doesn't react with any compound. So that is the reason that we use such a compound as a to produce the reference signal. Now let's understand that how do we interpret a spectra produced by a compound, and then we study the structure of various compounds, because the NMR spectra is going to produce different signals in the spectrum of a compound. Now the position of the signals is what we call as a chemical shift. So different hydrogen is going to produce a signal at different chemical shift. Also, we study the intensity of the signals, because intensity of signals gives us the number of hydrogen present responsible for that peak. We also study the splitting pattern of the signals. Now I'll explain you here that what do we mean by the splitting signal, but then what kind of splitting do we have for the signals? We may have a doublets, triplets, quadrates or multiplets. Now what is a doublet? A single peak, rather than producing a single peak, may split into two signals. Now this is called splitting of signals into doublet. Now as a single peak has split into two parts, we call it as a doublet. But if it splits into three signals, a single peak splits into three signals, three parts, then we call it as triplet. And similarly, if it splits into four parts, then we call it as quadrates. And if it further splits, we can call them as multiplets. Now how is this splitting done? Suppose if a carbon have a hydrogen and this hydrogen is going to produce the signal, but the splitting of this hydrogen will depend on what? Will depend on the number of hydrogen atoms on the adjacent carbon atom. Now for example, here this hydrogen is going to produce a signal, but its splitting depends on the number of hydrogen atom on the adjacent carbon. So suppose here the adjacent carbon have two hydrogen, so the splitting of this particular hydrogen is going to be 2 plus 1. So this hydrogen is going to produce a triplet as I have shown here. So a splitting depends on the number of protons on the adjacent carbon atom. Now if a hydrogen is surrounded by two carbon and it has many other hydrogens, so suppose here this hydrogen is surrounded by two carbon with total of 5 protons, so such in splitting will be 5 plus 1, that is 6 splitting will be seen. We can call this as a multiplet also. So the splitting depends on the number of proton on the adjacent carbons. This part will be more clearer when we take that into examples. So let's go ahead with some more examples to study what are the different types of signals, what are the position of signals, the intensity and the splitting pattern. But before that, let's have a look at a table which shows that what kind of hydrogen is going to produce a chemical shift in what range of ppm. So here you can see that these are the hydrogens which are often alkyl groups, maybe methyl group of CH3, CH2 or a simple CH, but it's going to produce a signal, that is the chemical shift at the range of 0.9 to 1.7 ppm. Now here you can see that and carbonyl group is present. So a hydrogen besides the carbonyl group, a hydrogen bonded to a carbonyl group is going to produce a chemical shift in the range of 2.2 to 3 ppm. Now here you can pause the video and study this full table where the bold proton indicates the peak and it this hydrogen is present in which environment, that is, besides the hydrogen, what kind of other atoms and elements or groups are present, that will decide the chemical shift of such bolded hydrogen, and it will show you the range at which the peak will be produced. So a video can be paused and studied, but we will go ahead with examples. Here let's study the high resolution NMR of a compound shown here, but we call this high resolution NMR because we can see that here the peaks produced are split into triplet or singlet or multiplet. But if these peaks are only single, no splitting is there, then we call it as low resolution NMR. Such are low resolution NMR. But if the peaks are split, then it's an high resolution NMR. So here we are studying the high resolution NMR of one of the compound. Now here we can see that such a compound is a propanol. Now a propanol have how many kinds of hydrogen atom? That is shown here, that all these hydrogen are given the name A. Why? Because these three hydrogen are in the same environment bonded to a single carbon, and besides which is another carbon bonded to two hydrogen. So the environment of all these A type of hydrogen is same. The second type of proton is the proton named as B here, and this proton also. Both this proton are of the same environment because again they are bonded to a single carbon, besides which we have one methyl group CH3 and on the other side we have CH2. So both the environment of these hydrogen is same. Next, we have C type of hydrogen here labeled C. These two hydrogen are again in the same environment as I have described for the hydrogen type of A and B type of hydrogen. The fourth type of hydrogen is the hydrogen bonded to oxygen in the alcohol group. Now these hydrogen is again of different kinds. So how many types of hydrogen environment we have? 4. 1, 2, 3 and 4. So 4 types of peak we should get, and here also we have seen that there are 1, 2, 3 and 4 types of peaks. 4 signals we have got, which is again split into some splitting pattern. Now let's study this splitting pattern with what environment the hydrogen is surrounded into. Now if we study the A type of hydrogen, then we can see that it's a methyl group. Now if we have a look at the table which we have seen earlier, then this alkane, that is methyl group, should produce the 0.9 to 1.7 ppm range. So if we have a look, what is 0.9 to 1.7? This is the signal which we are expecting for A type of hydrogen. So 0.9 to 1.7. Now this splitting of the signal A. Now we can say that the fourth peak is produced by the A type of hydrogen here, and it is split into triplet. Now let's study why. This hydrogen, A type of hydrogen, have a carbon which is having 2 protons. Now as we have seen that the splitting will be 2 plus 1. So the carbon adjacent to such type of hydrogen is having 2 protons. So 2 plus 1, triplet splitting is present because the number of hydrogen present besides it is 2. So that's the reason that the fourth signal is responsible for A type of protons split into triplet. The next type of proton is B. Now this proton is having again a methyl group, so again it should be produced somewhere near 0.9 to 1.7 ppm itself, but this hydrogen have 2 carbon besides it, which is having 3 protons and 2 protons on each side. So total of 5 protons, and these 5 protons should be having a splitting of 5 plus 1, so splitting of 6. So such peak, the third peak here, the third peak and its splitting, you can call it as multiplet, and the peak, third peak, is responsible for the B type of proton, we can say. Okay, next, I hope these points are clear, that how come the peak A and B are producing the fourth kind of peak and the proton type of B produces third peak. The next is C kind of proton. Now the C kind of proton is again a methyl group itself, but then it is bonded to the alcohol group. So let's study that what kind of peak it should be producing. Now here we can see that an alkyl group bonded to oxygen should be producing a peak in the range of 3.2 to 4. So if we study our peak, 3.2 to 4 is this peak. So the peak number 1, 3.2 to 4 ppm range, and that is the peak number 1. Peak number 1 is responsible for the C type of proton, and it is again split into, we can see here it is split into triplet. Now what's the reason for this triplet? We can see that the C type of proton have a carbon adjacent to it with 2 hydrogen. So 2 plus 1, that is 3. So triplet should be produced for the type of proton 1 peak with the C type of proton. So this is how we have already seen the peak of A, B and C type of protons. Now the last proton which is left is the D type of proton. So let's see that the hydrogen of an alcohol produces what kind of peak. Now here we can say that hydrogen of the alcohol should produce into the range of 0.5 to 6 ppm, a very big range. So hydrogen of the alcohol can be produced in any range of this. So here the peak number 2 is responsible for 0.5 to 6 ppm, that is the range for the alcohol hydrogen, and it is the peak number 2 which is produced by this type of proton, and we can see that that's a singlet. Now we should remember that all the alcohols or the hydrogen of amine group, all this hydrogen will always be producing the singlet. Why? Because it is not bonded to carbon, first point, and so we don't have to consider the proton of the adjacent carbon. So the protons of hydrogen and amine group is always going to produce a singlet. So this is how we can study the high resolution NMR of some compounds, and here we took a type of alcohol. Now let's study one more example which will make all these points very clear. Now one more high resolution NMR spectra is given for an organic compound, and the question in the board exam may be something like this, that suggests the structure of an organic compound for the given NMR spectra. The molecular formula is given with C4H8O2. Now with O2 kind of compound, what are the possibilities of that kind of compound? It can be a diol, that is 2 alcohol groups can be present in that compound, or it can be a carboxylic acid, that is COOH group, or it can be an ester with an RCOO-R group. So such possibilities are there with 2 oxygen in an organic compound. So let's have a look at all these possibilities. But the first thing we need to remember is that we have C4, but the number of peaks produced are what? There are 3 peaks. And the number denoted here gives the number of protons responsible for this signal. So the first signal as here is responsible for the 3 protons, that is 3 protons is going to produce this peak at a range of about 1.3 something, and the second peak, which is a singlet, is also produced at 2, but then 3 protons are responsible for such a peak, and the last peak, which is approximately at about 4.1 or 4.2, this peak is produced by 2 protons. So the number of proton is also given in this NMR spectra. Now let's study the range and identify that with 4 carbon atom, what are the possibilities and what is the structure possible. Now if here is a carboxylic group, if the carboxylic group is present, then the hydrogen present in the carboxylic group should produce a signal in the range of 9 to 13. But in our spectra we had seen that the highest peak range was approximately at 4.1 ppm only. So this has reduced the possibility of carboxylic acid. Now what are the possibilities left is either 2 ols or the ester group. Now if an ester group is present, then we should get a peak of this range 2.2 to 3, and again another peak with 3.2 to 4 pm. Why? Because then in an ester group we will have C double bond O also, and a single bond O also bonded to some methyl or ethyl group, alkyl group we can say. So that is the reason that we should get 2 different peaks in the range of 2.2 to 3 or 3.2 to 4, or alcohol in a big range. Now let's study our spectra. Yes, we have got 1 peak in the range of 3.2 to 4. So here are the possibility of a C or proton bonded to O group. So here confirms the possibility of the ester group. Now why would I say ester, not the diol? The reason is that, as we have already seen, that if there are 2 hydrogen of an alcohol group, then it should produce 2 singlets, 2 different singlets, but here we have got only 1 singlet. So that again reduces the possibility of 2 alcohol groups. The carboxylic acid have also gone. So now we are left with only 1 possibility, and that is the ester group. Now ester is having the 4 carbon atoms. Now what is the possibility of this 4 carbon atom having an ester group? Now let's study the first peak. It says CH3 group is present and its splitting is a triplet. We can see here it's a triplet. That shows that this CH3 is, now I'm drawing this ester group here, should be bonded to a carbon having 2 hydrogen, because then 2 plus 1 will give a triplet splitting. Okay, so CH3 bonded to CH2 is confirmed here. Now there is another peak with 2 proton. Now this is the possibility that is split into quartet. Here we can see that. Now quartet again shows that these 2 hydrogen is bonded to a carbon with 3 hydrogen. Therefore it gives 3 plus 1, that is a quartet peak here. So we know that there is a CH2 group also which should be bonded to CH3 group. This gives together the possibility of CH3 and CH2 group being simultaneously besides each other. Now let's have a look at the table again. As we can see that quartet had a range of 3.2 to 4. So this should be bonded to the oxygen atom directly. So this shows that the two proton responsible for this peak, that is this proton, two protons should be directly bonded to oxygen. So this is how a ester structure should be. Now as I have erased the other part so that the diagram doesn't become too messy, so let me draw again a CH3 bonded to CH2 group which is directly bonded to oxygen. Now we are left with one more peak here with a 3 hydrogen peak which is a singlet, and so CH3 is possible with a singlet. Now what's the range? Its range is approximately 2 to 2.1. Now what is the ester group having? Ester group should have a CH3 or any other alkyl group bonded to C double bond O. Let's have a look at the table again. So here is this CO group, alkyl group bonded to C double bond O with the similar range 2.2 to 3. So here again we have the similar range 2.1. So we can say that the 3 hydrogen here is bonded to C double bond O. So here we should have a CH3 bonded to C double bond O. So in other way we can also draw our ester as CO O CH2 CH3, that is ethyl ethanoate is our structure. So this is how we study the high resolution NMR of given compounds. So keep watching more videos to see more examples of NMR. We will be very soon discussing some more past paper questions for NMR so that you get a good practice.